Okay, let us, everyone, have your attention for another few minutes to finish the experiment. Brady has gotten his numbers for the inductance, and for the capacitance. So what numbers did you get, Brady?
For inductor, 14.03.
Units of henries.
Yeah. And then for capacitor, 8.44 nanofarads.
Okay, so those are the values Brady got. Now let's check. This actually has things written on it, if I can read them. This says 13.6 henries for the inductor, so you can see that he's in the ballpark there. And for the capacitor, I see 20%. I can't really read it. So I'm hoping that Brady's answer is right because I can't really read it. So what are we going to do with this? It says to obtain values for L and C. Are your values going to be the same as Brady's? No, because everybody's graph is going to be slightly different. Those two arcs being very similar in radius, it's going to be a fair amount of deviation from one person to the next just for tiny variations in your graphs. So I don't expect everyone to have the same values. So don't fret about that. The next step is to find the resonant frequency. Well, the resonant frequency is the frequency where XL equals XC. So if I set XL equal to XC, I'm going to set 2 pi FL equals 1 over 2 pi FC. And just solve that for frequency. So I'll divide everything by 2 pi L. And then multiply everything by F. And that's going to give me on the left-hand side F squared. And on the right-hand side, one over 4 pi squared LC. So now I just need to put that in the old calculator. Square rooting both sides, the resonant frequency is 1 over 2 pi square root of LC. So we're going to use Brady's numbers and assume they're correct, and then we'll check and we'll see if they're correct. Notice I did get lazy and drop off the units. If you multiply L by C, the units of henries times farads, will give you units of seconds squared. So do you have it for me?
I got 462.5.
So 462.5, and the units are 1 over seconds or hertz. So that's our theoretical resonant frequency according to Brady. So what I'm going to do is take this number and I'm going to say, let's round this to something that's kind of, an even number. So I'm going to round it to 500. It's not exactly 500, but that's in the ballpark. So I'm going to say approximately equal to 500 hertz. And then I'm going to choose my frequency start is equal to F naught divided by 2, which of course half of 500 is 250 hertz. My frequency end is equal to 3 halves F naught, which is going to be 750 hertz. And my delta frequency is going to be F naught divided by 10, which is 50 hertz. Obviously, I chose these numbers to make my life easier, right? If I would have done 462.5, I would have had harder numbers to type in. And I just want to get the numbers. I don't want to spend a lot of time doing it. So now that we have that, we can actually take the data. I don't want to look at all of the voltages now. I only want to look at the voltage on the resistor. because the voltage on the resistor is proportional to the current. So I'm going to turn off everything that's not, oh, come on. Everything that's not the resistor. The resistor was, nope, the resistor was A. I actually was right the first time. So I'm only going to look at the voltage across the resistor. I'm going to set my frequency, so I'm going to just start at down. It's pretty hard typing on this, it turns out. 250 hertz, and let's see what we got. So and it would be nice if this would automatically measure it for me, but no such luck. Whoops. So I need somebody to actually record this data for us because, well, you all need to record it because it's your data. So you should have a table that has frequency and voltage across the resistor. And at 250 hertz, we have 1.70 volts, plus or minus 0.01 again, same reasons as before. It's 250 hertz, you see at the top, and 1.70 volts, plus or minus 0.01. Okay, then I'm just going to go up by 50s. So, come on. 300. You see at 300, it went up, right? And so that's at 300 hertz, 2.11 volts. And now we'll go to 350, maybe. Went up again. Okay, so that's 2.68 volts. $400. $3.32 volts. $450. 3.79 volts. $500. 3.83 volts. $550, it went back down. 3.49 volts at 550. $600, down some more. It is 3.05. $650. It is 2.68. $700 is 2.36. And 750 is 2.11. Now, where was our peak?
500.
Okay, around 500. So I'm going to go back to 500. I'm going to try to get a little more detailed data at 500 to see if we can find better where the peak is. So let's try 525. Come on. Okay, so 525, it's 3.664. That's below 500, right? So let's go to 510. So 510 is 3.77.
Lower.
That's lower as well. Okay, so let's try 490. It stopped. Don't know why it stopped there. Okay, so that's 3.83 at 490. So that's the same as we had. Okay, so let's go down to 485 and then up to down to 485. 3.87. That's the same as well, isn't it? That's higher?
Yeah.
Okay. So then let's go down some more to 480. Well, as far as I can tell, that's the same. So go down some more. 475. Wow. It appears exactly the same, doesn't it? Okay, there at least we can see it was down a little bit lower at 450, but there wasn't much change there on that side. So now we have data that we can plot to plot the voltage as a function of frequency. And where you have the peak voltage is where you have resonance. Now I'm going to actually show you a graph using Excel. I have to actually change computers, so that's going to